What is up?
What's going on?
I am excited. Trey, I do not know how to identify storms. I'm hoping I've come to the right place.
It is good. I will be able to tell you what a storm is by the end of this.
That is awesome to hear. Anna, are you also excited to learn what a storm is?
I am beyond excited.
That is good. That is very good to hear. Go ahead and turn on my camera. Bless you all with my face. What do we got going on in the chat tonight? Anna, you already okay, so did you have to request to speak, Anna, or did it just let you come up on the stage?
I do a request to speak, and then I put myself on the stage.
So you like shake your own hand, basically?
Yeah, pretty much.
That's weird. All right. Jen Kushner says, I don't know how to identify them either. Cool beans. I received a message from Trey earlier today. Um, Despite the fact that I told him these sessions were going to be a little more relaxed and kind of more like a podcast interview, he went the extra mile because that's just what Trey does. And he has a lot of visuals, a lot of stuff he's going to show you folks, bring up on the screen. So, Trey, I'm really excited to see what you've got cooked up here.
Yeah, this was basically I'd already made the outline for the storm spotting foundations module, and then of course we kind of switched things up. So this is basically just the outline from that. Obviously, not going to go as in depth as maybe a module tonight, but I've got a pretty much a visual example for all of these things that we're going to talk about. So that should be good.
Yeah, and I think that it'll work out really well that way just because the entire premise of storm identification is quite literally the visual element, seeing what it
Yeah.
is the storm actually looks like. So, probably no way around it. Really glad that you were able to prepare like this. And for all of you who are wondering, because we have got a few questions about this, we are going to do something. I don't know if it'll be a complete storm identification training module. If you folks have read the emails that we've been sending out, all of the Chaser Academy content that we had previously created is going to be dripping out slowly on YouTube starting in 2026, so in a week or so. And whenever that's exhausted, we'll kind of take a step back. We'll look at what the Storm Chaser coaching, I guess you could call it almost like situation is, and we'll figure out the best way to move forward with the content. But rest assured, we will have something a little bit more, we'll call it evergreen, that you can reference on the YouTube channel at some point down the road. But this will hopefully be a more than reasonable stopgap measure for those of you who are looking to learn about storm identification before you go out and chase storms in 2026. So, without further ado, Trey, I see that pre initiation is the first bullet point that you have listed here. And how is it that we are supposed to determine whether or not a cloud in the sky is going to turn into one that's severe, or is it one that we can just brush off and wait for the next one to pop up?
Yeah, so what we're going to do pretty much tonight is go through the entire process of a storm. So we're going to look for things pre-initiation from the cumulus field all the way through to the mature stage. Give you some signs not just of things you need to be looking for when the storm is ongoing, but before the storm has started. So we're going to talk about basically pre-initiation to start, and we'll see how this goes. I don't have a set presentation for this. I've kind of just put all the images ordered as I'm going in a folder. So we'll just kind of pop that up. It looks like I don't have the ability to share my screen. Are you able to turn that on for me?
You're a moderator in here, so if you look along the bottom, you should see like leave the stage, unmute music, share screen, turn on camera, mute. The desktop picture with the arrow on it will be the share
Okay.
screen.
Okay.
Does it give you that option, Trey?
Yeah. I was
Okay,
looking in the
cool.
thing at the bottom left for the stage, and it wasn't allowing me. So let me see if I can get this to go here. All right. All right. Do you see the screen there?
Yeah, a little SCCception.
So
And echo.
is everybody able to um, maximize that size? Is there
Yes.
Okay, everyone
If you
can do
just
that?
click on it, then it'll full size it.
Okay, perfect.
I am hearing an echo though. I don't know if you have earbuds that you can put in, Trey.
It's Are you hearing your own voice? Is that why? 'Cause I'm
Yeah.
in my
It's just because he's streaming the Discord page.
Yeah, I will let me stop sharing the screen and I'll
Actually, wait. I should be able to mute it from my end. No, I can't.
let me try it again and I'll turn the audio off.
Okay.
Not that I have anything audio to share, but I turned on the setting where it shares the screen audio just in case.
Okay. Yeah, that's
All right,
better now. I can't hear my perfect.
All right, we'll see. I'll go once this pops up again. There we go. All right, so we're going to start pre-initiation here. And so obviously the starting point here, can everybody see the image there on the screen? Just making sure you can see the sky image there.
Yes, we can.
Okay, perfect. So this is basically what you want to see for when you're before the initiation has occurred. Obviously, we're looking for cumulus, and they may not develop right away. You may have to wait a while for cumulus to actually develop. I've chased setups where you have blue skies for much of the day, and then finally, once the forcing starts to arrive, cumulus start to percolate. But you want to see cumulus. You don't want to see an overcast stratusy sky that's really kind of gray and featureless. That's not good. And this is a good example. This was from the Alta Vista Day last year. This is actually from the Chase and Explain, but you can see over here as I start looking to the south, you can see all of these cumulus they're nice and bubbly here. They've got a little bit of vertical growth to them. Again, we'll get to that once they start going vertical here in a second. But you want to see this, just a broad field of these kind of puffy cumulus. Not really a ton of stratus or altocumulus around, but these nice kind of low-level cumulus is what you want to look for. And then I pan here going over to the north, and you can see a fairly stark change in the overall nature of the clouds here. So you can see as I go to the north, you can see a lot more of these kind of flat gray clouds, not really a ton of vertical development here. That is a much more stable sky and not really indicative of one that's going to favor robust convection. You can contrast it to this nice puffy cumulus, to this very flat, sort of featureless gray cumulus. That's not quite as good for initiation. You want to see something like this, a nice broad cumulus field. And again, you want to see these cumulus be sort of puffy. You don't want them to be very flat. We're trying to get toward vertical development. A nice broad cumulus field indicates that you have broad scale forcing for ascent going on over the region. There's kind of stages to forcing. You have your large scale forcing for ascent that's acting upon the region. That gets you, it's kind of just the broad scale, sort of subtle lift from an incoming trough or something that allows the atmosphere it kind of primes the atmosphere for initiation. And then once we get a source of more focused ascent, like a boundary, dry line, outflow boundary, surface convergence, etc., then that's when you're going to see the cumulus become more and more vertical in nature, and that's going to be when go time is going to be. Speaking in kind of this cumulus realm here, I'll kind of give you some more examples of kind of what good cumulus are going to look like. So you see here, just nice puffy cumulus, not a ton going on, but still you see some vertical extent to these. Here's another good example from Wyoming a couple years back. Just a nice broad cumulus field, lots of cumulus, not a ton of that kind of crappy stratus that's just flat and gray. You have a nice surface insulation going on with these puffy cumulus. That is what you want to see pre-initiation. Going on.
Now, Trey, but before you go any further, I do have a question.
Yeah.
So you're talking about that crappy like stratus deck that can ruin the day sometimes.
Yeah.
Is there any situation or situations where you would pay less mind to something like that versus when you would pay more mind to it?
So theoretically, if you think about it, if you have an environment that's been destabilizing for most of the day, you've had a lot of sunshine, your temperatures are getting pretty warm, and then you have a cirrus deck move over, theoretically, you would think that shouldn't be too much of an issue. If you reach your convective temperature, storms are or storms are able to go up in as a cirrus deck kind of comes over, it shouldn't be a problem because you've already reached convective temperature. But I will say anecdotally, I have never really seen a setup work out regardless when there's a thick deck of cirrus. And I'm going to kind of show you an example here. This image was from the infamous May 26, 2021 day, the Benkelman, Nebraska day up there. Things went off on the surface low, down the dry line. We got skunked because of this. You can see this very expansive cirrus deck. Here's our storm that was trying to go up in western Kansas. And then this thick cirrostratus deck just moved in over the region. And once I saw that, I knew we were screwed. Now, again, you were able to get storms to go up, so you would think it shouldn't matter. But I will say I've really never seen a setup work out when you have this thick cirrus deck. So I've seen situations where you have kind of, you see this a lot in the southeast, where you have just a kind of a broad area of cloud cover over low level cloud cover over the region, and maybe some thinning of that doesn't really fully get into cloud breaks, but you have just some thinning of that. I've seen storms go up in that. But if you have these scenarios in the plains, especially where you have this cirrus deck, I've really never seen it work out. Another example was one of the day, I believe it was April 1st of this year, the day before the big April 2nd outbreak in the Mid-South and Southeast. The day before that, it was a big risk in Oklahoma. There was a tornado risk. Models were showing supercells, but we never cleared up. We had this big deck of cirrus clouds that overspread the region pretty much throughout the day. Updrafts were able to go up, but they were completely elevated. And we'll talk about elevated versus surface-based features coming up. But I have never seen a setup work out where you have this kind of thick cirrus deck. So this is not something you want to see. Even if storms are going up, anecdotally, I've never had that work out, unfortunately, even though theoretically you would think it might work out. So
now,
going,
Trey,
yeah.
what causes cirrus clouds like that to form? We know that cumulus clouds are caused by parcels of air at the surface rising and then condensing. But those cirrus clouds, where do they originate from? What do they indicate about what's happening in the atmosphere?
So it depends. It just means that there's some high level moisture going on, and this can come from a few different sources. This can be anvil overspread from storms that are well out to the west of your area of interest. The anvils are kind of sheared out to the east, for example, over your area of interest, and that can kind of cloud things over. Also, you can just have sort of high level moisture that might outline where the forcing is. A lot of times you will see, if you look at satellite imagery and whatnot, you might see some subtle cirrus clouds moving in as the trough is moving into your area of interest. So it can be a good thing, especially if they're just wispy, kind of broken cirrus. That's the distinction here as well. Wispy, broken cirrus, you just see a few cirrus clouds. That's not a bad thing. That's not going to thwart your destabilization at all, really, in most cases. But when you have this thick cirrus deck, this cirrostratus, this layer of cirrus, and just stratus clouds or overcast in general, that's going to be the thing to watch out for as a red flag. But it can also be a good thing, cirrus. It can outline where the forcing is. So if you are kind of struggling to figure out where a shortwave is on your upper air maps, cirrus clouds can actually denote where the forcing is. So it's just some high level moisture associated with a forcing mechanism like a shortwave, or it can be that anvil overspread. Those are probably your two main sources of those sort of cirrusy situations, if you will.
Awesome. Cirrusy situations.
Cirrusy
I like the sound
situations.
of that.
Yes.
So, Trey, I'll let you go back to it. You were going to talk about some other examples that you have.
Yeah, so going off with the cumulus field, I'm sure you've seen on satellite, many of you, these horizontal convective rolls. So these cloud streets, these bands of cumulus clouds. And, this is a decent looking sky, but you notice how these bands are organized or these clouds are organized in these very well-defined bands or streets of clouds. These are horizontal convective rolls, and the way these form, we talked about it in some of the modules previously, but the way these form, basically you have these counter-rotating vortices in the atmosphere, and in the ascending branch of the circulation, so where the convergence happens, so you see between this one and this one, the winds are coming together, so you get rising motion there and you get cumulus clouds. Here you get sinking motion, so you don't get anything. If we had another one over here, you would get clouds over a cumulus street over there in the ascending branch of the circulations. So that's how those horizontal convective rolls form. But they're an indication of stability. And you're going to see a theme as we go through this, that the more sort of symmetric or laminar or shapely, if you will, these features are, the more that has to do with stability, lingering stability in the environment. So anytime you see these horizontal convective rolls, and of course this is a very well-defined example. This one here maybe not as well-defined, but you can still kind of make out the bands of cumulus making up those horizontal convective rolls. This is a situation where your atmosphere is likely still capped or it's still stable. And if storms try to go up in an area of horizontal convective rolls, you're likely going to see it remain elevated because there's still some capping in the environment. But in a lot of situations, you'll see that storms might go up, the horizontal convective rolls will dissipate through the afternoon as you get continued destabilization, and then it's off to the races. So always keep an eye out for these horizontal convective rolls, as they mean that you still have a little bit of stability in the environment to deal with. And then going kind of along this sort of theme, I don't have a great picture example for this one, but sometimes you can pick out boundaries visually with your eyes in these situations. And that usually is going to be just a scenario where you'll see a broad cumulus field, but you'll see some more well-defined, maybe more vertical cumulus, kind of oriented in a band or line, and then you might have just some less defined clouds around it. Or maybe you don't see those at all, and you just see kind of a line of these cumulus, just one single line kind of bending or arcing in a certain area. That could be a boundary, and of course you'd want to back that up by looking at surface data and maybe radar, for example. But that can be a good thing as well, and that's something that I have seen in many situations. Of course, you can see it on satellite. For example, here, this is the Chapman, Kansas day. You see that very well-defined boundary on satellite. If you were at the surface staring up at that, you'd be able to see cumulus clouds kind of formed in a band, an arcing band along that boundary. So that's another thing to watch out for, is those boundaries. We know what boundaries can do. They can help in the tornado threat with a given setup. They can actually help storm initiation in a given setup. So always keep your eye out for those boundaries visually. Of course, again, backing those observations up with satellite or surface data or radar data as well. So that's kind of the pre-initiation stuff. Now we're going to get into sort of initiation and what you should look for as storms are kind of going up and as they're trying to mature. So the main thing you're going to look for is you want to see vertical growth. You might see some attempts that go up and kind of die off, but you want to see these, of course, again, nice cumulus field here, but this particular updraft is going much more vertical now. That indicates that the cap is decreasing. That also may indicate that your forcing is starting to fully arrive, especially your more focused forcing is starting to act on that environment and actually allow for convective updrafts to become more mature. Now, as these, here's another example. Of course, you see clouds going vertical within the broader cumulus field. That's a sign that initiation is underway. Now, as the storms are going up, you want to look for some signs that the storms are struggling. So, for example, here's a struggling updraft. This was from the day this past spring where I think it was a 10% unhatched in Oklahoma along an outflow boundary, but there was no forcing, no synoptic scale forcing for ascent. Storms tried to go up at sunset, and then one storm went up out by Hammond and Arnett in far western Oklahoma after dark. No, there was a lot of chaser convergence that day, but this was one of the initial updrafts from that day. And this is a telltale sign. This updraft is displaying telltale signs that it is still struggling. First off, you see the kind of soft edges here. Very soft edges, not really well-defined edges here. They don't really have that crisp cauliflowery look. Compare that, and I'll actually load this up here with something, what I call a rock-hard updraft. So compare that updraft that's struggling to this updraft. Very crisp, well-defined cauliflowery edges there. It's got that real cauliflowery look to it. This is an updraft that is not struggling. There's not really any factors in the environment that are holding this updraft back, whereas this one very much struggling still with becoming mature, and that can be from a number of things. This is a lot of times a look of dry air entrainment or struggling with capping, especially if the updraft becomes pinched off or narrow. You see how narrow this updraft is and kind of pinched off at certain points. that is indicative of dry air entrainment. The air is ingesting dry air. It's kind of evaporating some of that cloud mass on the sides of that updraft, and it'll give you that kind of pinched in look that's not indicative of a very healthy updraft. So if you see a skinny updrafts that don't really have those crisp edges like this one has, very soft edges as we call them, compared to this one, which looks very, very crisp and healthy. Those are some signs that your updraft is struggling. If the updraft is falling over, if it's extremely tilted, that could also be a sign that your updraft is struggling. So here is an example of that. So this is from the June 20th event. This is from Chris Gullickson of Tempest Tours. He shared this video with me. But just watch the updraft here. So here's your updraft. Very skinny. You can see it's very, very skinny in nature here. But look how tilted this updraft is. That updraft tilt is pretty extreme. This is often a sign that there's still capping in the environment. The atmosphere is not fully destabilized yet. You'll see this a lot in scenarios where maybe we've had some morning precipitation and it didn't really burn off as fast as you thought it would, or you have a very stout, just warm air layer aloft that's kind of prohibiting things from doing much. When you don't have a ton of instability in the environment, or less instability than you might think than the storm needs, and you have a very strongly sheared environment, that's going to almost cause these updrafts to topple over and get this really, really tilted look. And sometimes they may actually just become shredded completely and not really be able to become mature before they kind of topple over. That usually means that the shear is kind of winning out. It's certainly tilting the updraft, but the updraft doesn't have enough vertical sort of momentum, if you will, to really work with that shear to become a robust updraft. So these really tilted updrafts are usually not a good sign for your overall environment. Usually means that you're dealing with some capping. So yeah, once again, signs of dry air entrainment, those pinched edges, those wispy kind of edges as well, not really that cauliflower look to it. If the updraft's very skinny, that's another sign that your updraft is struggling. Or if it's very, very tilted. Also, if you see orphan anvils, that's also not a good thing. That means your convective initiation attempt has sort of failed. An orphan anvil is when the updraft goes up, but maybe capping has pinched off the updraft, and the actual anvil separates from the updraft. So you see your kind of remnant updraft out here, and the anvil will just become orphaned. It no longer is attached to the actual updraft and just kind of floats off as a little blob of cirrus moving out in the environment without an updraft to it. That is a sign that there's still capping in the environment and that your updrafts are going to struggle.
So it's little orphan anvil?
Yes, orphan anvil. Yeah, you'll see those a lot of times in the first, with the first attempts of a setup of convective initiation. You'll often see they'll go up, they'll kind of orphan out, and then they'll try again. And I'll actually have an example of that. You don't just want to see that happen one time and then that's it for updraft attempts. That usually means that the environment's going to really struggle to produce anything meaningful. But this is also a time lapse of the actual Spiritwood storm from the June 20th day. And this is from initiation, before initiation, going through when the storm started to become mature. So you see here, we're starting to see our updrafts go vertical. So that's a good sign. But you'll see that these updrafts, these attempts kind of struggle. And you can see this kind of cirrusy blob here. That's an orphan anvil. So the updrafts are going up, but they're getting choked off by the convective inhibition that's still in the environment. So the anvils become orphaned. They float off away from the environment. But the good thing about this day is we had a source of more focused ascent here to allow for multiple attempts. You'll see multiple vertical attempts going up here. They are not successful until the end of the time lapse here, when you see this one go absolutely nuclear right there, and that was the one that finally took off. So this is a good sign. This means that your environment is still trying, even though it might not be destabilized fully yet. If you have these repeated attempts in the same spot, even if the first few are kind of unsuccessful at convective initiation, the more attempts you have, it's just like shooting jump shots in the NBA or in basketball. The more you shoot, the more you're going to make. The more updraft attempts you have, the better the chances are that one of those is going to take hold. And of course, this was an example. And this particular attempt was the one that went nuclear, and the rest was history from there. So always keep an eye out for the multiple attempts in a given area. If you only see one attempt and it's continuing to struggle and doesn't quite get to maturity, and then that's it, that's probably not a good sign for your environment. But if you see these multiple attempts, that's a good sign that things may just not quite be ready yet for full-on initiation. So just keep your eye out for that. And then the signs of a healthy updraft. Once you have your updraft push that's gone up and has become sort of not quite mature yet, but you can tell that it's an attempt that has that it's
It
going to
seems to be
make it.
sustaining itself, right?
Yeah, that's a good way to put it. There are a few things that you want to see. The first one is a flanking line. So the flanking line is a string of sort of lesser updrafts that are trailing from the actual main updraft. So in this case, you can see here, main storm out here, and then your flanking line is right out there on the right side of the image. You can see there this kind of band of cumulus emanating from the main updraft. That is your flanking line. Generally, it's going to trail off to this. If a typical supercell here in the U.S. moving from southwest to northeast, it's going to trail off to the west or southwest or south or something like that. It's going to be, again, that train of updrafts going in. That means that you have multiple areas of uplift and ascent going on into your updraft. And this flanking line, the updrafts in the flanking line can actually feed the updraft. So if one of these updraft pulses within the main sort of a storm die off, you can have these other updraft pulses within in the flanking line kind of feed into the main storm and keep that storm alive. So you generally want to see a nice, healthy flanking line with your supercell.
Is that where we get cyclic supercells from? Is those multiple updrafts that are trailing behind the main one?
It is a mechanism for it, and sometimes you can even see some unique tornado genesis cases with that, where you'll see, I forget which one. One of the recent cases that I studied, I can't remember exactly which one it was, but you saw multiple updrafts going into the flanking or from the flanking line feeding into the storm. One would die off, and actually the next one would become robust, and then it would take over from there, and it produced tornadoes just like that. Nudging mechanism, yes, not necessarily in the colloquial or in the common sense that we think of, but it's kind of a different process, but you can think of it in kind of the same manner, that the next updraft is going to take over and kind of nudge the entire system that is the storm toward tornado genesis. And I see your question, Gabe, back here. What's the best way to identify large-scale subsidence from the backside of the shortwave that moved through sooner than expected? If you see your cumulus field dying off, that's not a good sign. So if you had a cumulus field in place that looked good, but then all of a sudden the cumulus start to dissipate, that's a bad sign. That usually means that there's some type of convective inhibition or sinking mechanism that is plaguing your environment. That's usually a bad sign. So yeah. I also see another question up here. Can updrafts punch through the cap and become significant? They can, especially if you have a stronger forcing mechanism. So of course you want your cap to erode as much as it can in most situations. A little bit of cap is not a bad thing because it can allow for a more discrete storm mode. And it can allow for a cleaner sort of evolution. But if you have enough forcing for updrafts to punch through and kind of, so that's what it really is. So if you have a capped environment, but you have a forcing mechanism, let's say like a cold front, that's going to be a mechanism that will push those air parcels up through that capping inversion to allow for them to become significant. Now, whether or not they're surface-based, that may remain a question in that case. But, if you have a forcing mechanism, more focused forcing mechanism, that can allow for updrafts to become mature, even if there is a cap. June 20th was a great example of this in North Dakota. There was obviously still some convective inhibition lingering for a while, as the first supercells were quite elevated, but those updrafts were able to go nuclear. Basically, they were elevated, so they actually, sometimes will actually go up and be rooted above that capping inversion. So they may be elevated for a while, but they can transition into surface-based from there. All right, so a healthy updraft usually has a flanking line, usually has a back-sheared anvil. That is also a good sign of a robust storm. So back-sheared anvil is basically when the anvil is spreading out into the ambient shear or the ambient upper level winds. So in this example, I'm looking at the storm from the northeast side of the storm. So if the storm is going up here, I am looking at it from this direction. So the storm is kind of moving right at me in this case. So the shear is kind of oriented in my direction, so to speak. If you imagine winds at the surface are out of the south, and then winds aloft are out of the west or southwest, you're going to have that shear vector that's going to be kind of pointing in my direction, or sort of toward the northeast or east, whatever it may be in this scenario. But you can see that the anvil is going back toward the west here, this portion of the anvil. That's called back shearing, a back sheared anvil. And that's always a good sign that your updraft is very robust. When the anvil starts to spread out into the upper level winds, into that shear, that tells you that you have a very strong updraft. So a back sheared anvil is a very good sign. You might see some knuckling on the underside of the back shear. So these kind of not quite mammatus-like features, but these little sort of pouch-like features on the underside. It looks kind of like knuckles on your hand. That is also a good sign as well. And really knuckled, back sheared anvil is a very good sign that you have a robust updraft. Again, multiple updraft pulses, that's a good thing. Something like an overshooting top. Overshooting tops are indicative of a very strong updraft because the overshooting tops are the result of the updraft punching into the stratosphere. We know that in the troposphere, where most of our weather happens, the temperature tends to decrease with height. So that allows for an unstable atmosphere. So your updrafts are going to go up. But once they hit the stratosphere, that's when that anvil spreads out. That's when the temperature becomes or increases with height. And so we lose that instability. The updrafts can't really go upward into the stratosphere very much. But if you have a very, very strong updraft, the momentum from that updraft can carry it a little bit extra into the stratosphere, into that layer of temperature increase with height, and you get this overshooting top. You can see it very well on satellite. We did talked about that in our satellite module, but this is what an overshooting top looks like visually, this nice little dome on top of the anvil. That is a good sign that you have a very robust updraft. Most of your strongest supercells are going to have an overshooting top, and going with that, pileus is also a good sign as well. So pileus clouds are these little sort of wispy caps on top of a developing cumulus. And so this is kind of the zoomed out view. This is the zoomed in view. So you can see these little pileus caps here on top of the developing cumulus or developing thunderstorm. And this is a good sign. These little layers of moisture, as the updraft kind of marches into more stable conditions aloft, you get these kind of these little more ice crystal type developments can actually form on top of the updraft. And that also indicates a very strong updraft. That's kind of, we talk about like gravity waves, for example. You throw a rock into a calm pond, that kind of expands outward. Those ripples expand outward. Same thing in the atmosphere. A thunderstorm that's really, or an updraft that's really robust, punches up through the atmosphere and into that kind of stable layer aloft near the tropopause and stratosphere. And then once it sort of spreads out, you can get these sort of features on the these pileus caps on top of the cumulus. So that's an indication of a very strong updraft as well. So an overshooting top, pileus cap, flanking line, back sheared anvil, those are all signs that your updraft is extremely strong. Can you have a flanking line and an inflow tail? So yes, that is going to be a little bit of a separate thing. So if you imagine your radar view here of a supercell, your flanking line is going to kind of come out sort of this way, back this way, and your inflow tail might come from another direction, maybe say from the east. So you'll have your inflow streamers coming into the supercell from that direction, or from this way. So yes, flanking line is a separate thing from an inflow tail, and we'll talk about the inflow tail here in just a second when we talk about actual supercell features. And speaking of that, we'll actually get into that right now. Here is another example, a couple more examples before we go on of what you're looking for, what you should look out for when the storm is maturing. So of course, here is that updraft, rock hard updraft, very crisp cauliflowery edges, very puffy cumulus look to it. Your kind of classic strong thunderstorm look. Here are a couple that might not be so great. You can see the difference here. This is a developing thunderstorm, looks great. But you can see how this one, not quite the same. Very soft edges here. You don't really see that real cauliflowery look to it. This is a view a few minutes later. Certainly producing some rain and maybe some hail in there, but notice how very ill-defined kind of edges here. Very sort of wispy, soft edges, and you can clearly see the difference between this and this. This ended up not really doing much and kind of fizzling out after an hour or so, while this one went on to become tornado warned in South Dakota. So always keep an eye out. You want to see those real rock hard updrafts as far as your most robust storms go. All right, so now let's move on to actual supercell features. We'll just kind of run through these, and of course, nothing is going to take the place of experience out in the field. You need to be out in the field, going and looking at these storms, trying to identify these features, and once you practice that a lot, you'll get better at it. And I will say, not every supercell is going to have all of these features. So don't make it sort of a checklist and try to check those boxes every time, because not every storm is going to be the same. Not every supercell is going to have all of these features, but that doesn't mean it's not going to produce significant severe weather. Just not every storm. Every storm is different, and that it depends on things like how much precipitation is producing. Is it an LP storm versus a high precipitation storm? Stuff like that. But these are the things yeah.
I was just going to say real quick before you move further away from that point, which I think is a great point that you made. Not every storm is going to have all of the features. And when I was first starting out, that was definitely something that threw me for a loop, because at least when I'm in the learning phase, I am a big like checklist oriented person.
Right.
So it's like inflow tail, check. Multiple updrafts, training into the storm, check. And I kind of found my balance by determining that if I could figure out like one or two features on any storm, so not figure out every, but if I could figure out one or two, then I could kind of get my orientation, my bearings on the storm, if you will. And it made it much easier for me to then figure out where everything either is or should be if it was present, even if it's not present. And that kind of gave me the freedom to roll with it even when everything wasn't there, if that makes any sense. So it's really like I just try to figure out where one or two things are. That gives me my orientation, my situational awareness, and then I can start kind of from there building out the rest of the storm and figuring out what I'm looking at.
Yeah, that's a good way to do it. I'm very checklist oriented as well. I want to see all those boxes checked. It's just easier for my brain to comprehend. But in an imperfect science like meteorology and storm chasing, it's not that easy, unfortunately. And I've seen many storms that don't look all that great and don't have a ton of these features still produce great stuff. And I've seen storms that look incredible and have a lot of these features not produce good stuff. So it just depends on the situation. Knowledge of the environment is also another thing that you should have. Of course, if you have a real good looking storm, but maybe your surface winds are extremely veered and you don't have any low level shear, well, you're not going to be wanting to look out. You're not going to expect to see a lot of those features that we associate with tornadogenesis in those environments, because your environment just doesn't support it. So you need to have a full comprehensive knowledge of the situation, the environment, and the actual storm features to have the best chance of having the most successful chase. So yeah, that's well said. We'll start simple here with the feature that you'll see a lot, and this is more of a classic supercell type thing. You're not going to see this with a high precipitation supercell per se, but that's your rain-free base. And you'll see this often in the if a situation does warrant more of a high precipitation mode, you'll see this initially when the storms are kind of going up. So your rain-free base is, as the name suggests, the broad base underneath the updraft. It's the bottom of the updraft that's displaced from all the precipitation. So in this case, you can see that all the precipitation has been shunted off to in this case, I'm looking due north. So all the precipitation shunted off to the east of the updraft, and then you have your rain-free base right there. You want your rain-free base to be nice and textured. It have a nice ragged, textured look to it. Again, we're going to go through elevated versus surface-based visual clues here in just a bit, but you want to see that nice, ragged, textured rain-free base. It has that kind of roiling motion underneath it, and you again want to see that precipitation displaced from it, and have a nice, clean rain-free base for your more classic supercells. So here's another example of a rain-free base. You see, once again, just very nice and ragged, has some lowerings underneath it, and all the precipitation. This was a storm that was actually moving to the south, and so you see all the precipitation is shunted off to the north of the base. We're looking north here, so all the precip back here, the rain-free base to the south. And how the rain-free base forms, it tells you that your environment is adequately sheared, that your updraft is tilted and the precipitation loaded downdraft is being displaced from your updraft. So your updraft is going up here, displaced from your downdraft. That's a sign that you are going to have a healthy supercell. Pulse thunderstorms, monsoon thunderstorms in environments of very weak shear, they're not going to oftentimes have this sort of rain-free base at least not for long. You'll see the precipitation falling very close to the updraft, and of course that is not good because that cool rain, that cold sort of rain-cooled air is going to interfere with the warm, moist air that needs to be fed into the storm to make sure it's a mature storm. So that's why supercells last a long time, because the updraft is displaced from the downdraft, and you have nice, warm, moist inflow going into that updraft, denoted in the rain-free base here. Of course, we can have scud underneath the rain-free base, so those little cloud fragments that are detached from the actual base. And you want to see with those scud fragments, you want to see them rising into the base. If they're kind of neutrally, their motion's kind of neutral, they're just kind of sitting there, it's not usually a great sign. You usually want those scud tags to be moving up into that rain-free base, into the updraft, as that tells you have strong rising motion ongoing within and below that updraft, and that's a very good sign. So those are a couple examples of rain-free bases. Always good to see rain-free bases when you are looking at storms. Does venting have anything to do with a rain-free base? Yes, that's exactly what exactly what fuels the rain-free base is the wind shear in the environment, the way the winds are constructed in the vertical or organized in the vertical. That's going to tell us where that precipitation is going to be vented. But generally, if you have adequate wind shear in the environment, you're going to see those updrafts tilted. The precipitation is going to be displaced from the updraft. So really, venting and the direction of the wind and strength of the winds aloft, that tells you where the precipitation is going to be vented. But as long as you have adequate shear, that's going to be you're going to often see a rain-free base, at least in the early stages of an environment. Again, if you have a high precipitation supercell environment, you might not see the rain-free base for long. It might get shrouded in precipitation. Those are your kind of weaker shear environments, more inadequate venting in those situations. So it definitely is related. So we talked about that. So next, I see another question here. How thick are the anvil clouds after they spread out, and why doesn't precipitation fall from the anvil? It depends. I don't have an actual number for you as far as how thick they are, but they can be somewhat thick. They can also be fairly thin. If you get a glaciated anvil, which means you have very kind of an icy fringe to that anvil, up top, they can be very kind of a thin layer of ice spreading out away from the storm. But sometimes you can get a decently thick layer of cirrus within that anvil. And precipitation doesn't always fall from the anvil, but you actually can get some rain from the anvil as it moves off. So I've experienced a couple times where you have orphan anvils above, and actually precipitation reaches the ground. So precipitation can fall from the anvil. But it is, I guess, somewhat unusual for it to reach the ground. All right, so we talked about rain-free base. Let's talk about the vault now. So we talked about this in the navigation module a little bit, but the vault is kind of this tall, ragged side of the updraft, and it's sort of the rain-free, precipitation-free area just adjacent to it. So your updraft is going up here, tilted updraft, and on this side of the updraft and this kind of rain-free region, that is the vault. And the vault is, if you were to look at a supercell on radar, the vault is going to be located in the inflow notch between the updraft. So if we had a classic supercell, your updraft kind of looks like that. So it's going to be kind of located in the inflow notch between the core of the updraft and the precipitation core of the storm. So it's in between those two. So if you have a typical kind of northeast moving supercell, the vault is usually going to be on the north or northeast side of the updraft. So in this case here, this was the Arnett day from May 18th of this year. We're looking due west at the supercell. Storm was moving off to the east-northeast or northeast, and here is your vault region on the kind of north side, north or northeast side of the updraft. And so the vault is visual evidence of the bounded weak echo region. So the bounded weak echo region is that region on radar of limited reflectivity aloft, surrounded by greater reflectivities. That tells you have a very strong updraft. It's kind of pushing or centrifuging those hydrometeors or raindrops and hail out from the center of the storm onto its periphery, so that you get that kind of precipitation-free or low reflectivity region in the core of the updraft. So it indicates a very strong updraft. And there's not really any significance to it as far as going being a precursor to tornado genesis or anything, but it is something that you need to pay attention to when you're storm chasing because it can have very large hail in it. So as the bounded weak echo region occurs, you'll get at the top of the beware is going to be something called the echo overhang. So the updraft goes up, you get your beware, and you get your echo overhang right in here. And this is when the updraft kind of chucks out all that precipitation away from it on the other side of the vault region into the precipitation core or downdraft. But on occasion, if you have very large hailstones, may not be able to make it all the way into the downdraft and actually may fall in the vault region of the supercell. So if you're on the north or northeast side of a developing supercell with a vault region, always be on the lookout for extremely large hail, as that can be of course, very dangerous for chasing. Here's another example of a vault. This was the Sulphur, Oklahoma tornado on May 9th, 2016. Again, we're looking west-southwest at the ongoing tornado right here, and the vault region is going to be on this side. So this was a northeastward moving supercell as well. So that vault region is going to be right in here between it, the updraft, and the precipitation core. So just a couple examples of the vault region there. Again, no real significance as far as tornado genesis goes. Not every supercell you're going to be able to see the vault, especially based on where you are relative to the updraft. But it is a sign that there could be large to very large hail falling, and some of the largest hail, albeit sporadic, can fall in the vault region of the storm. So always be mindful of that. All right, that is the vault, and of course, is a precursor to tornado genesis is often going to be a wall cloud, and of course, the wall cloud is evidence that the mesocyclone, or rotating updraft of the storm, is descending into the lower levels, or is developing in the lower levels. So it's going to be this blocky sort of feature underneath the updraft base that is generally, of course, for tornado genesis purposes, we want to see a rotating wall cloud. You can have non-rotating wall clouds as well. Those are not going to be of much interest. They can, of course, start to rotate, but if you have a non-rotating wall cloud, that's usually just a conglomeration of scud that's kind of reached the updraft base, and there's not really any low-level rotation to speak of. But if you have a nice blocky feature underneath the updraft base that is rotating, that is a sign that the low-level mesocyclone is developing and or strengthening. And not always going to be as obvious as this. Of course, the wall cloud, this is kind of the first signs of a wall cloud. Nice rain-free base right here. Once again, you see this little kind of lowering right there. That is the start of a wall cloud. It's not a very fully fledged wall cloud like the first image there, or this image here. Obvious wall cloud there underneath the base. And of course, if I had video of this, you would be able to see that this was rotating very rapidly. This was on the Dodge City Day in 2016, for those of you wondering. But again, it's going to have this kind of blocky shape, and for tornado genesis purposes, we want to see that it is rotating. Here's another example of a wall cloud.
Trey, real quick question about wall clouds.
Yeah.
So you've shown a couple of examples, and each of them look different. Obviously, that's always going to be the case. But is there a particular type of wall cloud, or like using like the definition from before, like the updrafts that are super crispy versus they're kind of ill-defined on the edges? Do certain wall clouds, do they indicate tornado genesis might be more near, or is it just they all have their own personality and you can't really pull anything away from that?
Yeah, not necessarily. Every situation is going to be different. Some tornado situations don't have a wall cloud. They just form kind of from a flat-ish base. Arnett was kind of like that. Not really any wall cloud to speak of. Whereas some situations you'll have a huge wall cloud like this. And I've seen some situations like this where you have a huge wall cloud and it doesn't really do anything. The real main thing that you want to be looking out for with these is you want to be sure that it is a rotating wall cloud. There are lots of imposters out there, and particularly those that turn into shelf clouds. So when we're trying to differentiate between a wall cloud that may become tornadic and one that it might signify more outflow dominance or more of a shelf cloud type situation, we want to be looking closely at the motion. So of course, with a wall cloud, you want to see rotation, left to right motion. That is going to be your sign that it is a rotating wall cloud. If you see the cloud matter just kind of moving in one direction or pushing out towards you, that is a sign that it is more of an outflow dominant situation, a feature that is fueled by outflow and therefore more of a shelf cloud type feature. And that can be tricky at first, but you'll here are a couple of examples. So this was, of course, the Beaver, Oklahoma day back in 2023. You can see the left to right motion of this wall cloud, indicating that it is rotating rapidly. So this easily could have produced a tornado. This was certainly a rotating wall cloud situation. Here's another one right here. Canadian, Texas in 2015. I'll speed it up here a little bit, but you can see the spin in the wall cloud. Doesn't maybe look like all that menacing of a wall cloud. It's kind of broken and fragmented, but the key here is the rotation. And this went on to produce a tornado just a few minutes later. You can see the left to right motion of this wall cloud, indicative of a low level mesocyclone. In contrast, if you are looking at something like this was on the high risk day from last year. At first glance, looks like a wall cloud, and I'll show you some still images here as we first pulled up onto this supercell near Waynoka, Oklahoma. This is what it looked like. So, if you were inexperienced or, just looking at a still image, you might think, especially this one here, it's attached to the base. It's definitely lowered from the base, so it might be sort of a wall cloud. But if you were to look at it, and you can kind of see it becomes more fragmented here, not really as blocky. That's kind of another distinguishing characteristic as well. It doesn't look as blocky, have that real sort of blocky, put together look. It looks more sort of fragmented and stretched out. That is an indication of a shelf cloud, more of an outflow dominant feature. You compare that to something like this. Looks real blocky. It doesn't look kind of strung out, fragmented. It looks real put together and blocky. That is a sign of a wall cloud. And of course, it's difficult to explain in words. You have to look at a bunch of wall clouds and shelf clouds and be able to get good practice at this. But again, you'll see it mostly coming at you. And let me turn the sound off here.
Yeah, that's something, by the way, Trey, that I'm glad you went over that. It was going to be a question I was going to have later. When I was first cutting my teeth chasing, I had a really difficult time parsing shelf clouds from Boeing RFD segments. Mm-hmm. And like you just pointed out there, some of the wall clouds that take on more of those shelf cloud type features. It can definitely be a bit overwhelming at first, which, if I could just throw this out there, another good reason to maybe just keep your distance, especially when you're first starting to chase, because if you're near that portion of the storm, that's definitely where the action is, and you don't want to be misidentifying storm features and putting yourself at risk.
Right. Exactly right. That is something that I think a lot of newer chasers struggle with, especially just taking a quick glance at a storm. If you were to look at this, you would say, "Oh, that's a cool wall cloud," and that the storm might become tornadic. But if you were to look closely, you could see it just kind of pushing out. There's not a ton of rotation here. This was a short clip. This is the best I could find. But you can see it's more just pushing outward. It was more pushing outward, and I can tell you because I was there, it was pushing outward. It didn't have any side-to-side motion, left-to-right motion. It was just coming at us, and that's a sign that you have more of a shelf cloud, even though it's attached to the base, even though it looks kind of like a wall cloud. And some of those other images we saw, it looked a little bit more strung out, less blocky, not quite as put together. And so that's a telltale sign of a shelf cloud. And also, that comes with the environment. Are your cloud bases high? Are you more likely to have outflow dominant storms, drier, low-level environment? That's something also goes back to having a knowledge of the environment is critical in these situations as well in identifying some of these features. But of course, visually, you can identify a wall cloud versus shelf cloud versus by looking for rotation versus single direction motion. And the overall look blocky versus more fragmented and strung out and elongated, so to speak. I did see a question in the chat here real quick. I know Skip Talbot talks about looking for the horseshoe at the rain-free base. So we're going to get into that here in just a second. I assume he means the clear slot, and we're going to talk about that here in just a second. So we'll get to that in just a minute. First, though, let's take a look at the inflow tail. Pretty self-explanatory what an inflow tail is. So the inflow tail, of course, here is your healthy supercell, rain-free base, very low rain-free base here. But this sort of tail feature that extends from the rain-free base and from the updraft base, that is the inflow tail. And that, of course, you want to visually see the clouds in that inflow tail streaming into the storm. There can be some of these sort of roll cloud looking things that may not be either attached to the base or they may not actually be getting sucked into the storm. A storm with a good inflow tail Number one means that your low levels are moist, because that means your clouds are condensing in that low level inflow stream. So you have a moist low level environment, and you have strong inflow going into the storm. Of course, strong inflow is usually a precursor to tornado genesis, especially if it's balanced well with just the right amount of outflow. Going back to things like nudger theory and whatnot. But an inflow tail is always a good sign to see. And sometimes it may not be kind of symmetric and laminar like this. Sometimes it may look more like an alligator's mouth. It's kind of what we call this feature here, an inflow tail that looks really ragged. So this is our storm, and then this portion right here, that is your alligator's mouth. And I don't know if that's a term that's been coined per se, an official term, but I've heard a lot of chasers use it. I've used it forever. It's the alligator's mouth. It's when you get all of this kind of ragged looking inflow that looks like the mouth of an alligator. You can see it kind of right there. That is a good sign, and I've usually seen this when alligator's mouth with the most beastly storms. And now that there's no science to back this up, but I've seen lots of supercells that produce tornadoes and really good structure, and just beastly supercells overall. They'll tend to have these more alligator's mouth type inflow regions, inflow tails. So always keep an eye out for that.
I've noticed a lot of meteorology is people who are around storms often saying, I don't have any evidence for this, but I've noticed that pattern a lot. And then years later, there's research done to confirm that what everybody was seeing actually ends up being a real thing.
Yes, definitely. Maybe one day we'll study the alligator's mouth and see what happens from that. But yeah, there's a lot of storm chasing, and good storm chasing comes from experience and pattern recognition and feature recognition. Not always explained by science yet, but there's certain things you see with tornadic supercells over and over again that we haven't really focused scientific research on, but they're always there. So there's probably something there. We just don't know exactly what that is. So maybe one day we'll get a little bit more clarity on these, but anecdotally, yeah, alligator's mouth, I've seen them usually with more beastly supercells. Not to say that a not beastly supercell is just going to have a more measly inflow tail, so to speak. But as long as it has a good, healthy inflow tail sucking into the storm, that's usually a very good sign for a healthy supercell. All right, let's talk about the clear slot. So the clear slot is the rear flank downdraft. I saw your question in the chat there, Gabe, about RFD strength, and this kind of would probably be your main mechanism here is the clear slot. Now, it's not always cut and dry like this shot here, but it is this cutout, this horseshoe-shaped cutout in the rain-free base. So this is a good example. This is another example here, base of the storm here, and just a nice cutout of kind of clear air that is indicative of the rear flank downdraft. So basically what happens, how a clear slot forms. So let's say we have our supercell. Draw a quick little anvil here. I know that looks kind of measly, but here's our supercell, precipitation falling here, and we'll say our wall cloud underneath. So what happens is the air aloft, the strong winds aloft, encounter the supercell, and it acts like a mountain, a barrier. The air can't go through the supercell. So what happens is it gets ingested into the supercell and gets brought down to the surface, and then it hits the ground and spreads out, and that's the rear flank downdraft contribution that we need to usually balance out the strong inflow. And at the interface of the rear flank downdraft gust front and the forward flank downdraft gust front and the inflow, that's where your tornado tends to form. So it's usually a very critical process. The RFD creation is a critical process in tornado genesis and supercells. And the way you can see that is by a clear slot. Now, it's not always going to be cut and dry like this, as I said. This was an example from May 6th, 2024, the high risk last year. And you can't really see a super well-defined clear slot. But if you look closely, you can kind of picture the features of a supercell. So we've all seen those diagrams of a supercell on kind of radar. You have the rear flank downdraft gust front. You have your forward flank downdraft gust front. And then you have your sort of inflow right here. And at the interface of that, that's where your tornado tends to happen. Well, you can kind of see this if you're looking into the inflow region of a supercell. So for example, here, not a very well-defined clear slot. There is kind of one right in here maybe, but it is a little bit shrouded in precipitation. But you can see the developing circulation right here, that lowered area, wall cloud. This is a very well-defined wall cloud here in the rain-free base. You can see the rear flank downdraft boundary right here, this kind of laminar cloud kind of feeding into the wall cloud and sort of wrapping around the circulation. And then you see your forward flank gust front. And of course, I'm drawing it in kind of a 2D sense here, so it's a little bit hard to tell, but you can kind of see the wrapping around of the rear flank downdraft around the circulation, even though there's not a super well-defined clear slot. If in a perfect world, we would have that nice horseshoe right there of more clear air showing us that the rear flank downdraft is coming down to the surface and wrapping around the circulation. But the clear slot is usually going to be a precursor to tornadogenesis in a lot of cases. Not always. The clear slot's not necessarily a mechanism where you can see the strength or the thermal characteristics of it. As we know, kind of colder RFDs tend to be less favorable. Colder, wetter RFDs tend to be less favorable for tornadogenesis, whereas warmer RFDs tend to be better for tornadogenesis. Not always going to be able to see that from the clear slot, but the bottom line is that when you see a clear slot developing in a supercell, that means that the RFD process is starting and reaching the surface, and that is a precursor to tornadogenesis. So always look out for the clear slot developing. It's usually a good sign that your storm is getting more mature and ready to possibly start producing. And again, it may not be always clear cut like this example here. It might be more like this, where it's a little bit more cluttered, but always kind of visualize what the boundaries from the storm, on that you might see on radar visually. So again, your wall cloud, your developing circulation, rear flank downdraft boundary coming out here. You can see kind of a clear slot there coming down to the surface, and then your forward flank precipitation gust front there ahead of the precipitation core kind of feeding, and at that interface right there, that's where your circulation is going to develop. So clear slot is very important in tornadogenesis processes. So why does the upper air colliding with the storm that ultimately creates the RFD travel downward when the air in the storm that it's colliding with is moving upward? So it basically, draw this again. So you have your updraft here, and this is, it depends on the thermal characteristics of the environment. So if it's kind of warmer, it should be a little bit warmer than the air in the updraft and near that precipitation core, because you have hydrometeors up here in the updraft as well that can tend to cool that down. So it might be a little bit warmer. It continues to warm as it goes down. It sinks subsidence, sinking motion. It tends to create warming as well. And of course, that's all relative. You can have pretty cold RFDs. It's all environmental characteristics, which is beyond the scope of this video, but it will wrap around and kind of sink and warm as it does so, and then it reaches the ground and it tries to induce tornadogenesis. There's a paper from Klemp at Klemp 1987 that goes through this mechanism a little bit better than I can. There's some math with it as well, some fancy math with it as well, but it has to do with the subsidence with that air, with the airstream in the RFD. Okay, elevated versus surface-based. This is a big one. I get a lot of questions on this all the time, but surface-based storms are typically going, I'll just kind of open all these up for us here. So surface-based storms are going to have more of that ragged, textured look to the base. So here's a classic example of a surface-based storm. So here is your rain-free base, precipitation vented off to the north. In this case, again, we're looking due north, so it's vented off to the east or northeast of the rain-free base. But if you just take a look at that base, very, very ragged, very textured underneath that base. You see some scud fragments, some lowerings in the base there. That's usually a sign that your storm is surface-based. Here's another example as well. Again, here's your base, a little bit of lowered area in the base, but it's got that ragged look to it. It's got some texture and features to it, indicative of a surface-based supercell. Here's another example. Again, a nice stout rain-free base with that wall cloud developing, features underneath the base. That is indicative of surface-based supercell. Compare that to something like this. This is more of an elevated supercell. Notice how we're not really seeing a ton of features in the base at all. It's very smooth, very laminar in nature. That is a classic sign of an elevated supercell. Here's another example here. Again, very, very laminar, very smooth features, kind of featureless base there. Not really a ton of that cauliflower look to the updraft. Here's another example, very, very kind of cold looking. Oftentimes you'll get sort of these blue tinge, this blue tinge to the environment. It looks kind of cold. You know, you imagine a film that's set in the winter. It kind of has that whitish, grayish, bluish tint that they put on the video footage to make it really seem like it's in winter. Well, it kind of has that here in a lot of elevated supercell cases that are undercut, dealing with cold air at the surface. Very laminar, kind of elevated or bluish look tinge to it, and different from more a hail tinge that's kind of bluish green, but it's got kind of that cold look to it. Again, it's very hard to describe in just words. You need to kind of see these out in the field to really get a grasp on these. But you can tell the difference between an elevated supercell like these that are very laminar, featureless, to this one that's surface based that has that nice ragged base, nice features, scud, lowerings in the base there. But we can also have, and of course, elevated comes from convective inhibition. Your storm is undercut by cold air, a stable layer in the low levels. Well, they're not always mutually exclusive. You can have surface-based storms when there's still convective inhibition, and usually that's going to result in storm structure, striations. So something like this. This was April 19, 2023 in central Oklahoma. Of course, surface-based supercell here producing a significant tornado at this time near Cole, Oklahoma, but look at the bell shape of this updraft. There was a little bit of convective inhibition in this environment creeping back in. And of course, after dark, the supercell near Etowah and Shawnee, that took on a very nice bell shape. And a lot of these storms that have the pancake stack structure, just multiple wedding cake layers stacked, a stack of pancakes, that indicates that you have convective inhibition in the environment. But you can still overcome that and have surface-based storms. Number one, if you have a surface-based supercell moving into a more hostile environment, you can that surface-based nature can persist for quite a while into more hostile conditions. But there can also be forcing mechanisms and other things within the storm dynamically, like we talked about on June 20th, with that upward directed pressure perturbation underneath with a strongly sheared low-level environment. That can help overcome that. You still might get a structured, well-structured laminar or more laminar look to the storm, or more kind of pancake stack look to the storm, but it can still be surface-based as well. But a purely elevated storm is going to look very, very laminar, very featureless, not have a lot of features in the base at all, look kind of cold and outflowy, and you can kind of see the difference here. Here's another example of that. This was slightly an elevated supercell, kind of just that laminar look to it, not a ton of features in the overall updraft and updraft base, characteristic of an elevated storm. So again, it takes practice. And they're not convective inhibition and surface-basedness of a storm. They're not mutually exclusive. You can have convective inhibition and still have surface-based storms, tornadic storms at that. But there are these are kind of the main differences that you'll see visually with storms that are surface-based versus more elevated in nature. All right, getting close to the end here, just some signs of outflow dominance. So again, like we talked about, more of that shelf cloud look to it, more of cloud matter moving out in one direction towards you, usually, like this one here. You can see the kind of tail here just pushing outward toward our location. I'll play that again. It's not rotating. It's not moving side to side and spinning. It's moving out at you. That is a classic sign of more of a shelf cloud type feature, more outflow dominance. Again, the wall cloud versus shelf cloud thing, more blocky versus more fragmented, strung out, elongated type feature there. Also, if you see a rainfoot, that's also something to watch for as well, for more of an outflow dominant scenario. So rainfoot's something you'll often see in the desert Southwest in the monsoon season. But you'll see the bottom of the rainfoot, the edge of the rainfoot kind of bow outward close to the surface. So you get this kind of foot here of the precipitation shaft as it hits the surface. This is the strong downdraft winds hitting the surface and spreading out. It'll carry some of that precipitation with it, so you get that kind of bowed outlook like you see in this example here. That is a sign that the downdraft is very strong in your storm. And of course, a strong downdraft usually means strong outflow. And you'll see this a lot in high-based scenarios. But if you see a supercell that looks good, but you start to see a rain foot in the precipitation core, that could be a sign that your storm is tending to be more outflow dominant rather than more balanced or inflow dominant. So signs of tornado genesis. Of course, we talked about the clear slot, the development of a clear slot, the development of a wall cloud. A rotating wall cloud is good. And speaking of the motion of a wall cloud, you want to see that carousel type motion, really rapid rotation in the wall cloud, like a carousel, a merry-go-round. That is often a sign that your wall cloud's going to produce a tornado at some point. I've rarely seen motion like this, like you see here. You can see it visually. This is not sped up at all. You can see that wall cloud just cranking super hard. It's what we call carousel motion, that really, really rapid rotation. That is usually a sign that your storm is going to produce a tornado at some point soon. Of course, not always, but I've very rarely have I seen motion this rapid not produce a tornado. The Beaver, Oklahoma day that we showed earlier was one case where that happened. That was a special case. This one ended up producing a tornado a little bit after this footage here. But just a very stout wall cloud. You can see, again, blocky, lowered feature there, not elongated and kind of fragmented. It's very blocky, and it is rotating super hard. So that's a good sign, that carousel type motion. Wrapping rain curtains. Also be aware of wrapping rain curtains. This is from Kimball, Nebraska in 2023, late June 2023. You can see the rotation at cloud base there. Very rapid rotation. Once again, very strong rotation. Even though the storm was kind of high-based, that rotation was super strong. You could tell something was imminent. But you can see these rain curtains coming in from the left here, wrapping around the circulation. Of course, this is a situation where the tornado starts before you really see the rain curtains wrapping around the mesocyclone. But the point stands. If you see these rain curtains start to wrap around the area of rotation in the storm, that's a sign that the RFD is coming around, starting to wrap around your circulation. And that is often a precursor to tornado genesis, those wrapping rain curtains. So always keep an eye out for those wrapping rain curtains. And if you're engulfed in wrapping rain curtains, that could be a sign that you need to get the heck out of there.
That's what I was about to ask you, Trey.
Yeah.
I think a lot of people get too comfortable because they think it's just rain, it's just wind. But I know one of the lessons I learned very early on from Skip Talbot was if you are in any part of the circulation, just consider yourself as being in the tornado.
Yeah, that's a good way to think about it. Having some buffer is always a good thing. So if you're in any part of this, and you start to see wrapping rain curtains coming around you, and again, keeping a close eye on the direction of motion of these rain curtains. They may look like they're going in just one direction, but you can actually see they're kind of wrapping around. Of course, a little hard to tell on the video here, but they were legitimately wrapping around completely the circulation here. And if they're kind of rotating around that circulation, that is a sign that the RFD is wrapping around, and perhaps a tornado genesis is very imminent. So always keep an eye out for those wrapping rain curtains, and always give yourself an extra buffer, and you should be good. And then once again, of course, the clear slot. Always look out for a clear slot, and again, try to visualize those boundaries that we talk about often, that you see on a radar depiction or a schematic diagram of a supercell on radar. Try to see if you can point those out visually like we did. Here's your circulation. Here's your RFD gust front. Here's your forward flank downdraft gust front. And of course, your inflow at our back going into the storm. So our interface, our circulation is going to be right there. Matches up pretty well. And it could be tornado time, especially as this kind of clear slot and robust lowered area of the wall cloud starts to develop. So always keep those in mind. You also might see a lightning increase. That's not necessarily, I don't really have an example of that, but for those of you who have been out chasing close to intense supercells, you often will see a jump in lightning as the storm is maturing. It's called the lightning jump, and there's been peer-reviewed research on this. So you'll often see lightning start to really ramp up as the mesocyclone ramps up. That is the correlation there. As you see that lightning jump, usually it's going to be in the form of positive cloud to ground lightning bolts. So you'll see a lot more cloud to ground lightning bolts. They'll become more frequent. That means that the mesocyclone is increasing in intensity. So that could be a sign that your storm is about to go to undergo tornado genesis there. And oftentimes, interestingly, during tornado genesis and during the tornado, lightning will actually decrease. And that is probably something to do with size sorting and shear. I'm not 100% sure what the correlation is there. There are much smarter people on that than I am. But there has been some peer-reviewed research showing that lightning will increase in intensity and frequency leading up to tornado genesis. That means your mesocyclone strengthening. And then once tornado genesis happens, lightning will often decrease in intensity, or in frequency. So always keep an eye out for those. And then finally, just some other things to look out for: signs of dissipation. If the mesocyclone becomes exposed, so if you start to see your tornado become more carved out, and you can start to really see up into the storm, it kind of clears out a little bit, and you just see that long extended tube up into the storm. That's usually a good sign that you might be getting toward dissipation. And always look out for handoffs. Handoffs, of course, this comes with deviant motion as well. This was on the Dodge City day, but this was the old circulation there producing a strong tornado moving off to the north. And you see this wall cloud here out closer to where I was, here just off to its east. This was a new mesocyclone that was taking shape. So always look out for these dual mesocyclones and these handoffs, because this tornado eventually dissipated. It kind of moved off to the northwest, and then this one took over. So if you were underneath that second circulation and didn't really know what you were looking at, you could have been in a bit of trouble. So always keep your eye out for those dual circulations and how that handoff process works. The old circulation will dissipate, tends to move in a more deviant fashion, kind of off to the north or northwest, and then you'll see a new mesocyclone develop where the old one kind of was, and oftentimes that will undergo tornado genesis as well.
Now,
so you'll often,
when you have a handoff like that, is it typically considered a different tornado or the same tornado?
No comment, because I know where this is going. You know where I stand with that. But different tornado. Different tornado, same storm, different tornado. And we'll just leave it at that. But
Point taken. All right. You're the coach. Far be it from me to try to tell you how to run your session. I was curious. I was very curious.
I know. That's always sparks your curiosity. So I'm glad you asked that. But yeah, that's about it for me. So of course that might not be a cut and dry list of every single thing that you need to look out for when you're chasing, but those are the ones that you'll see most often. And again, don't use it as a checklist. Not every storm is going to have all of those features we talked about. But the more you see, the more robust your storm may tend to be. If you have that rain-free base, you have a vault, you have that rotating wall cloud with an inflow tail and clear slot, that's usually a good sign. So the more boxes you can check, the better. But that's not always end-all be-all. For example, cold core supercells, you're not really going to see a lot of this stuff. It's just going to be a tilted cumulus cloud with a tornado underneath it, maybe a flat base, and you're not going to see many of those features at all. So don't use it as a checklist and a cut and dry list of things to see. But a lot of your more robust supercells are going to have a lot of these features. So,
and just a reminder to everyone, you'll see on the left-hand side next to the premium group coaching stage, there's a channel that says group coaching replays. We take these sessions. You can expect it 1 to 3 days after the session, just depending on how busy we are. We take it, we actually get a complete transcript of the entire session. Then we create timestamp chapters. We upload the video to YouTube as unlisted, and then we put the link in the group coaching replays channel. So if you check over in that channel, you'll see not only is there a YouTube link for you to rewatch every session, there are also timestamps, and those timestamps will tell you where to go in the YouTube video, and also they're actually embedded in the YouTube video at the bottom, so you can scroll along, or you can go to the description and click on it. That'll be especially helpful for a group coaching session like this, where you're going to want to go back. Something will pique your curiosity when you're out chasing. Oh, I remember Trey talking about, this, that, or the other. You can go right back in this. You'll have Discord installed on your mobile device. and that magnifying glass at the top of the group coaching replays channel. In fact, the magnifying glass is there for every channel, but in this channel in particular, you can go ahead and click that magnifying glass and you can type in whatever storm feature it is you're wanting to get a refresher on, and it'll pull up all the different chapters that have that particular storm feature or those particular combination of words. And then you can quickly just click the video and you can, it's kind of like the roughest best way we could come up with of making the group coaching session something that could be archived and searchable without having like massive text documents in the channel. So just to give you guys a heads up on that in case you hadn't already heard about it, these sessions are all on demand, completely searchable, and you will have access to them years from now even. So don't worry about trying to remember everything right on the spot. I know Trey went over a lot of information, but you'll definitely be able to study this as you go along.
Yep, absolutely. That's the whole point. We want you guys to have this stuff for as long as you want to have it, because it's a lot to digest in just one session. So it's always good to go back and review, even just on some off time. Go back and review the concepts, and the more you expose your brain to that stuff, the more you'll be able to identify this kind of stuff out in the field, and the better storm chaser you'll be.
So, folks, we have about 7 or 8 minutes left. If any of you have questions that are related to this or something different that you wanted to ask Trey, and I'll just throw this out there, Trey, that you can chat while maybe people are formulating some new questions. Tell us a little bit about the recent video about fog that has apparently just blown up your channel. You wouldn't think, out of all the awesome stuff you talk about, everything from EF5 tornadoes to the Edmund Fitzgerald, it's a video about fog that just absolutely goes off. So yeah, tell us a little bit about that.
Yeah, it's now become my number one viewed video of all time. So it's
That's
just
nuts. That's
it's
freaking
just kind of
nuts.
funny how that works. But yeah, it was really interesting. I wasn't planning on doing a video on it, but I just kind of checked. I was scrolling through social media and saw some people mention it. I'm like, oh, that's pretty interesting. Looked at the satellite data, and it has been persistent in the Central Valley of California, that fog layer, for now going on 4 weeks, almost a month straight of just persistent stratus and fog in the Central Valley, which is just insane. It used to happen like this several decades ago, back in the 1900s, but has since decreased in frequency. These what they call Thule fog events in the Central Valley in the winter, they've decreased in frequency quite a bit since the 80s. So it's definitely something rare, and especially something of this duration. You don't really see that often anymore. And it's just a simple case of valley fog and radiation fog, where air at night, the air energy radiates from the surface back into space, and the air cools, and once it cools to the dew point, you get fog. And that can happen especially in valleys, and it's just a large scale version of that in the Central Valley. And it's just we've had such a stagnant pattern in the mid and upper levels with that high pressure ridge just kind of sitting there that fog has just not been able to lift at all. They had a little bit of sunshine, I think, yesterday. I saw some comments on the video. But I think looking at the satellite today, they were socked in fog once again. So we'll see. It's just kind of a vicious cycle there. The high has shifted a little bit farther south, so hopefully they can get some sunshine. But I see a lot of people in the comments loving it. I know I like a little bit of fog, but a month straight of it might get a little bit old. So, but yeah, that was that. Just kind of an impromptu video that's gone crazy.
When you live in California, where the weather is just almost perfect all year round, people who enjoy weather, this is like the only extreme weather they're ever going to see. So I'm sure that they're soaking it up.
It's true. It's definitely more like winter is typically for most people. And I know in California, they don't get that much unless you're up in the Sierras or the mountains, any type of mountains there. But yeah, I enjoy a little bit of fog, but man, 4 weeks of it would be a lot, and definitely would be a little bit depressing. So, but yeah, that was that. I guess I just need to be a fog specialist. That's where I need to go. Fog Chronicles, or I have to find some rhyming or some alliterative word with F. So,
yeah, well, it's the capturing lightning in a bottle with a current news event. Plus, I like the thumbnail you got going on there.
I thought about the current event thing. I thought it would have a better chance of taking off, but I thought it's still fog. Who cares about fog unless you're in the Central Valley? But I guess a lot of people do. So yeah, there'll
Yeah,
be
so
more of
from
those.
from doing a little bit of research for the Storm Chaser coaching YouTube channel, which is about to all of you listening right now, watching right now, it's about to pick up in a big way here at the start of 2026. Just been planning out everything meticulously. And one of the big things I found is that the algorithm gives like a huge amount of special treatment to people who cover live events, because if you think about it from YouTube's perspective, on a large scale, they're competing with other news networks. Even though they let like Fox News and MSNBC have channels on their platform, they're still competing with like MSNBC.com and FoxNews.com. And so whenever they can take a video from youtube.com that is about a current event and then put it into the search results up against MSNBC or Fox News or whatever they have, that to them is a huge boon for their company because it gets more people staying on YouTube as a platform instead of actually going to other websites. So definitely something that if you folks are out there with YouTube channels and you're thinking about ways to potentially grow your audience, maybe throw in, if it makes sense for the type of content you create, some stuff that's centered around current events, because you have a much, you at least, it's not a guaranteed recipe for success, but you definitely have the algorithmic gods at your back, so to speak. If you're throwing something like that out there, you won't be fighting against the current, at least.
Yeah, very true. And I did package this one a little bit differently with the thumbnail. I couldn't really think of a way that I do my typical thumbnails, kind of less flashy.
Yeah,
So I just went for it and did the single satellite image with never ending fog. I maybe a little clickbaity, but whatever. It
I
worked.
like it. You're loosening up, man. You're letting your hair down a little bit. I
Yeah,
like this side of you.
yeah,
I'm
yeah,
appreciating it. I like to
yeah.
think maybe in some small way I've rubbed off on you a little bit, and for that I will
Maybe,
say that
yeah,
I'm pleased.
maybe a little. Yeah.
All right. Well, congratulations again on the best video you've ever had on your channel. May there be many more. May each one be a banger, as the kids say.
Thank you very much. We'll see. Hopefully, some more fog events. That apparently is what sells. So we need some more fog events to analyze. But no, back on the severe train coming up soon. I've got the finished the breakdowns for 2025, and then end of February, my 2026 tornado season forecast. Looking interesting early on here. Will we see 4 straight years of active tornado numbers? We'll see.
I sure hope so, since our business is built around that.
Yes, absolutely. Yep.
That'd be pretty nice. But
Yep.
all right, everyone. Well, we appreciate you joining us here tonight. It's been awesome. I learned a lot. I know all of you did as well. And remember, if you ever have any questions, you're always free to hit us up in support or just to shoot the breeze in the VIP lounge. You guys have access to it, so you might as well use it. And of course, your Q&A channel as well. If you have any questions that cross through your mind throughout the week, you're not thinking about it while you're here in the session with us, and then all of a sudden you're taking a shower or shopping for groceries and you're like, oh damn, I should ask Trey about that during the session. You can always throw that in the coach Q&A chat, and Trey or one of our coaches will definitely answer it as soon as they see it.
Yep, absolutely. I know the Q&A chats, the channel's been a little quiet recently. So definitely, if you have any questions ever on anything meteorology related or anything else, just fire them in that Q&A chat. We're always happy to answer.
Awesome. Well, I'll see you later, Trey. Thank you so much, Anna, for being our audience coordinator tonight, and all of you folks have a wonderful evening.
Thanks, everybody.
Alrighty.